Welcome.
Thank you so much for this warm welcome, and I'm so excited to be here. Wow, so many people. My name is Ekaterina. I am a senior data scientist at NVIDIA. Who of you here know NVIDIA? Just a quick check. Nice. Who of you knew NVIDIA 2 years ago? All right, many gamers here, I see. So I came here to Australia. It's my first time in Australia, actually. I love the country. I can say that after the week. I took some quokka selfies yesterday. It was amazing. So I came here to tell you about latest in multimodal generative AI. Multimodal generative AI is my major area of expertise as a data scientist. And I'm just curious to know, are there any fellow data scientists in the audience? Raise your hands. OK, nice, nice. So as a data scientist, I can tell you, I know how you've been feeling for the past 2 years. At least that's how I've been feeling for the past 2 years. So while some of us are still tweaking parameters of convolutional neural networks, the huge wave or tornado of generative AI is sweeping out everything on its way and even making some jobs obsolete. But before we continue with the more serious content, let me give a big round of applause to the sponsor of the event. Thank you so much for bringing me here. It's really, really awesome to be here and getting to know the community. So now, what is actually generative AI? Before we explore this question, let's take a look in the retrospective. And before generative AI, what we used to have was a huge variety of different network architectures. We used convolutional neural networks mostly for image processing. GANs were used for image generation. We had reinforcement learning, which was predominantly used for robotics. And RNNs, recurrent neural networks, were mostly used for language and text processing. A big issue with this approach is that to train such an architecture, you would need a data set which would be labeled by some experts. So you need to employ human experts to find objects in the images, to draw these bounding boxes around these cats and dogs. And once you have trained this network, it would be very good at doing one and only thing, detecting cats or dogs or any other object you was marking there, for example, in the case of convolutional neural networks. But you can imagine, if we want to have something like artificial general intelligence, this approach wouldn't be sustainable because you simply cannot label the whole world of objects or subjects. And I believe we've been doing the first steps towards this direction, towards the sustainable solution, and it is called multimodal generative AI. Multimodal generative AI is the new wave of AI. So we rely on an architecture called transformer architecture. Usually it's a big neural network consisting of billions of parameters, which has been trained on large scale of data to the scale of the whole internet. And you can imagine, you cannot label the whole internet of data. So these networks are trained in unsupervised fashion. And as you may have guessed from the title, Multimodal Generative AI, they rely on different sources of data. So it not necessarily needs to be text. It can be also images. It can be code. It can be video, sound, and all kinds of data format you can imagine. And then these networks, instead of just classifying images, instead of drawing bounded boxes, they actually are able to produce new content, hence generative AI. And the content they produce can be also of different formats. It can be text, it can be images, it can be code, videos, 3D, and so on. So it's a truly amazing technology. And this technology is being already super useful. This report, paper Sparks of Artificial Generative Intelligence by Microsoft, it shows you that the GPT-4, GPT stands for Generative Pre-trained Transformer, and it's the multimodal architecture produced by OpenAI. It is able to achieve zero-shot tasks. It's able to perform zero-shot tasks with the accuracy of 82%. So what do we actually understand by zero-shot tasks? Zero-shot means that you don't necessarily need to train a network for some explicit task. It is able to, for example, detect cats or dogs without specifically being trained for that. And we understand that by a zero shot. So 82, it's already not random. It's already a very good number, which indicates that these networks are already very useful. That's another example how these multimodal architectures are able to handle complicated tasks. So with my customers, I used to work on in the area of smart cities and smart spaces. And you may know that it's an important task to keep our cities clean and clear. And the task of visual pollution was a really hard task to solve for deep learning and AI. So detecting graffiti is one of such hard tasks. Now with multimodal generative AI, you just upload an image like this, and it's able to not only say, okay, there is a graffiti in this image, but it's able to precisely describe it, find its location, and also say what is actually special about this graffiti. Like in this image, you see it's a tricky one. It has some 3D effect, and the network has been able to identify that it says the artwork gives the illusion that the child is using the steps as a slide. So really impressive. The next one is a little bit scary. So when I just learned about multimodal generative AI, I was like, wow, can it actually solve CAPTCHA? Because in the past I was working in computer vision, and I know it's a very hard task for a machine. And surprisingly, it is. And well, luckily, this is taken from ChatGPT. The OpenAI, the creators of this, they put some guardrails. So usually it's not the case. You won't have it solved with ChatGPT. But for some reason, I've managed to jailbreak it with this example. Another great example how generative AI has been impressive is it's actually able to understand humor. So here in this image, you see a smartphone being charged by something which looks like a VGA connector. And they've asked it, hey, what is funny about this image? It was able to describe that there is a smartphone, there are 3 different panels in this image, and it was able to tell that, well, VGA connectors are usually not used to charge smartphones, which makes this image funny. In the next example, I'll show you how multimodal technologies can be used to enable you with the gaming experience of the future. So let's just take a look.
We are thrilled to showcase an immersive and dynamic interaction between a player Kai and a non-playable character named Jin. This captivating ramen shop scene was created by NVIDIA using the latest RTX rendering technologies. NVIDIA collaborated with Convey, an NVIDIA Inception partner, to showcase how developers will soon be able to use NVIDIA Riva, Nemo, and Audio to Face for AI-powered speech, conversation, and animation. These models were integrated into the Convey Services platform and fed into Unreal Engine 5 and MetaHuman to bring Jin to life. Please take a look.
Hey Jen, how are you?
Unfortunately, not so good.
How come? I'm worried about the crime around here. It's gotten bad lately. My ramen shop got caught in the crossfire.
Can I help?
If you want to do something about this, I have heard rumors that the powerful crime lord Kuman Aoki is causing all sorts of chaos in the city. He may be the root of this violence.
I'll talk to him. Where can I find him?
I have heard he hangs out in the underground fight clubs on the city's east side. Try there.
Okay, I'll go.
Be careful, Kai.
I think it's really impressive, and of course it was just a recording, but we actually have this demo running, and I saw it and tested it, and it's absolutely fantastic and fun to interact with it. So how does this technology work? I already briefly mentioned that we need to have a transformer architecture which has been trained on lots of data and has billions of parameters. And the model in the middle, we call it a foundation model. And also, the architecture called a mixture of experts is frequently used these days. So in this scenario, instead of having just one foundation model, we have an ensemble of these models which collaboratively work together on solving complex tasks. These models work with data of different formats, hence multimodal generative AI. And in the beginning, when we train these models, they're actually good at doing one and only task, is predicting next word in the text. We can actually expand it and teach these models to perform specific tasks by performing some fine-tuning operations. We call model customization fine-tuning. You can also think of that as task adaptation. And you can adapt these models to perform such tasks as generating code. Think of your copilots, which I'm sure most of you are using these days. You can use them for translation to different languages, to summarize content, be it a video, a text, or an image. These models can be adapted to perform image captioning or video captioning, to understand sentiment analysis, also in different data, in text, in videos, in speech. Typical chatbot applications, question answering, it's also a fine-tuned foundation model. And finally, typical computer vision tasks like object recognition, cats and dogs, object classification, object segmentation, body pose estimation. This all can be also achieved through generative AI. Now let's dive deeper into multimodal generative AI for images. This is my specific area of interest. And multimodal generative AI for images helps solving tasks like this. So imagine showing, our model, our generative AI model, an image like this, and asking it to write a description to sell this house. At first, it seems simple, but actually, it's a more complex task because it needs to understand what's in the image. The second task would be actually to write a description so that the person who reads this description actually wants to buy this house. So you need to format it as an advertisement. So it's not as easy as simply describing the image. So how do we achieve this? It gets a little bit technical here, but I promise you it's the most technical you'll have here. So at the top of it, you have a large language model, which basically used as the uniting large language model for images and text. And in the input, you need to provide images and text to teach this model. And for this model to understand images and text, they need to be in the same space. We call it embedding space. And basically, embeddings are just vectors representing some objects or subjects in the world of large language models. So we need to produce embeddings from our images, we need to produce embeddings from our text, and we need to map them on the same embedding space to be able for this large language model to be able to process them interchangeably. So to do that, we use our, first of all, our image. and we put another network called Vision Transformer on top of that. So what Vision Transformer does, it serves as an encoder. It takes our image, and image, as you know, it's also numbers, right? RGB numbers. We take these numbers, we convert them into the embeddings. And then we put a projector network on top, and the boxes marked in green, projector and large language model, these are learnable networks. And Vision Transformer are frozen. So after running this for many iterations on millions of image and text pairs, we are able then to achieve that if we upload an image to our network, we can produce a description in text. And then we can further adapt this text to produce like marketing advertisement, writing jokes, and even poems and songs. So we can be very creative here. But the essential step is bringing our images and text in the same embedding space. To give you a reference how much data we need that, OpenAI trained their similar model on 400 million of pairs of images and text. And you may be wondering now, I was telling you about unsupervised learning, right? But now I'm saying you need images and text. So the trick here is you can crawl these images from the internet, and you can use the HTML alt tags for the text description. Of course, in many cases, it won't be very accurate, but if you do it at scale, it will be enough to produce good quality content. Another great application of multimodal is image generation. And in this example, this was something which motivated me into learning that. I saw these apps which allow you to generate your own portraits, and I absolutely wanted to learn this technology to be able to do it on my own, on my workstation. So I've achieved that, and I'll tell you how it works. But before I continue, let's actually take a look at the multimodal use cases, right? So we have two categories of image generation, which is unconstrained generation. You can use it, for example, for portrait generation. It's very useful if you want to create some avatars to anonymize something. You can use it for synthetic asset generation, and this is very useful for something like a digital twin, right? So this is another popular area these days. Everything which can be simulated will be simulated, and for that you create 3D or 2D digital twins. And for that, you can actually rely on generative AI to creating content, to populating these virtual 3D worlds. This technology can be also used for super resolution. So imagine if you have a bad quality image, you can actually enhance its quality by applying these techniques. And there is a second category, are condition generation. Well, the first and the most obvious example would be you provide a text prompt, and then you expect an image or video or 3D being generated as you've requested in this text prompt. You can also apply selective image editing and in-painting. And I always like giving this example. Let's see if you have a photograph of you and your ex-girlfriend or boyfriend, and you want to edit them out from the picture, you can apply this technology to do that. And you can also use it for text-guided image-to-image. So let's say you want to start with some sketch, and you can further expand this sketch into something more realistically looking. A little bit of a history here. So this all has started in the year 2018. I remember I was visiting the conference CVPR where NVIDIA, I wasn't working at NVIDIA back in the day, NVIDIA has introduced the StyleGAN approach. With StyleGAN, they were able to generate perfectly photorealistic looking images of portraits, which was already very impressive back in the day. So it was relying on the GAN technology, a little bit of a different technology, but these were the first mature steps in the direction of image generation. Then the approach GAN has been introduced. It was used to generate landscapes. And then the new wave of diffusion-like approaches came. And I was absolutely mind-blown when I discovered DALL-E by OpenAI. It was roughly 2 years ago, a little bit longer than that. It worked like magic, so I'm sure many of you have experimented with that. So you enter a text prompt in the browser, and you get what you've just imagined. So it worked like magic to me back in the day. Then Google came with the Imagen approach, and then somewhat revolutionary in this field was the approach called Stable Diffusion. Its creators, they've trained their network, and they've released the weights of the model as open source. They've released their code as open source, which opened many, many doors to researchers from all over the world and democratized the technology. And now we have seen so many derivations of it appearing. So we have now text-to-video, we have now text-to-3D, and this is very exciting. And the quality gets better and better every day. So allow me to demystify this technology to you. How does it work? Here, we don't use just a single model, but it's a pipeline of models. And there are 3 essential components to that. The first one is CLIP. It doesn't necessarily need to be CLIP, but CLIP is one popular architecture which is used for that. And this is the component which allows you to take your text and map it to the image embedding space. And then the next 2 components are autoencoder to make this efficient, and the third component is unit. In the modern architectures, it's also sometimes replaced with the so-called diffusion transformer. But in this example, to simplify things, I will take a look at the more classic stable diffusion-like pipeline, which was relying on unit. So unit architecture. Unit is a popular architecture, and those of you who've been working in data science for quite a while, you may recognize it as the network which has been used for image segmentation. So it's a U-shaped architecture with scale down and scale up paths. And what you usually, in case of image segmentation, you would pass a pair of an image and an image mask to this network, and you would expect it to provide the segmentation mask on the unseen images in the output. Turns out that you can also use this architecture to predict noise in the images. So you have an input image, you have some amount of noise added to this image, and what you want to achieve, you want to predict the noise which you provided in the input. Now you all may be puzzled, why do we want to predict noise if actually all we want is to generate crisp and clear images, right? So apparently, if you predict noise many, many, many times iteratively, and you subtract it on every step, you can get from a very noisy to very crisp and clear. Let me show you this example. So to train such a network, you pick an image, and again, you need millions of images to train such a network. You generate some random noise, and you usually use some special schedulers for that, which means that you already know what kind of noise you're adding and what is the amount of noise you're adding, and you can use it for the supervision to train your unit. And then you add this noise to the image, and then you pass it, oops, I got stuck here, sorry. So you pass this amount of image, and you predict this amount of image. Inference is a little bit different when you compare to image segmentation. So in the inference process, those of you who worked with image segmentation, you know that you run it only once, and you have the segmentation mask. In this scenario, you generate the random noise, like in this corner of the image, and you do it iteratively, let's say 30 or 50 times until you achieve the nice and crisp and clear result. All this would be very computationally expensive if you would run it on HD images, right? Luckily, there is an approach which allows you to go from the full resolution images to a compressed, latent representation of these images. So for that, we need to rely on the architecture called autoencoder, or specifically variational autoencoder. And there we need two networks. One network would be an encoder network. And with this encoder network, what we do, we have our original image, we compress it in the latent space, and then we need to apply first of all, we do all the unit operations in the latent space, and then once you've produced your result, also in the latent space, you decompress it using the decoder component of your architecture. And you can imagine that training this decoder would be actually relatively straightforward, because what you expect in the output should be roughly the same what you passed in the input. Then this, what I've described, you would work for unconditioned generation. And I've mentioned that if you want to condition your network with some text prompts, you need to apply this essential component, which is called clip. So clip was originally introduced by OpenAI, and it allows you to map your image to the text in the same embedding space. How you do that? Well, as I mentioned before, crawl on the internet, you have the supervised pairs of image and text, and you pass your image through the image encoder. You get the numbers, embedding numbers. You pass your text through the text encoder. You also get your numbers. And you can imagine, they are coming from different sources, right? So these embeddings will be different at the beginning. And to bring them in the same embedding space, you need to apply the so-called compare function. We call it contrastive loss. And what this contrastive loss does, it basically rewards the pairs which were similar, and based on that, you update the weights of the network accordingly, and it penalizes the dissimilar pairs. So for that, you also need some negative examples. So once you have done it iteratively many times, what you would achieve is that you could use the image encoder and text encoder interchangeably, and they will produce embeddings in the same space, and they will be similar. So putting all the building blocks together, you have our image latent, converted with variational autoencoder. We have the noise amount generated by our scheduler. We have the text embedding, which we get from the text encoder. And then we have our unit, and then we pass all the information from through this unit. We also rely on the so-called cross-attention layers. Basically, these cross-attention layers, they allow you to fuse the image latent and text embeddings in the same embedding space, and then you predict the generated noise. You do it several times, and you get a nice and clear image. This also works for image-to-image generation. So in this sketch, there was my attempt to draw a pink panther, and you can tell I'm not a professional artist, but luckily I know generative AI, and I was sure I can do it, I can make it look better. So I took the sketch, and I asked it to generate a pink panther. So instead of initializing the image with random noise, I've initialized it with my poorly drawn sketch, and it produced me this nice result. And the beauty of it, if you're not satisfied with your result, you can see it differently, and then the noise will vary, and you can do it as many times until you achieve the result you're happy with. On top of that, you can actually prompt it into doing some other crazy things. So I saw, okay, maybe I can generate a cat, and it got me a cat. Still looks a bit like a panther, but then some friend of mine told me, well, it might look like a bear, and it actually got me a bear. But then I was like, okay, let's experiment. So it got me a monkey, a cow, and even a pig. So you can tell I had lots of fun doing this exercise. But going back to the topic which motivated myself into learning how it works, into experimenting with it, is creating artistic portraits. And this example, which I show you from the network, I fine-tuned myself, so I'd like now to demystify this process to you. What do we need here? First of all, again, we need our diffusion model. It could be unit, it could be diffusion transformer. We need our text encoder, and of course, we need training data. So we take the training sample, and we have its description, and we add this special tag into this. So you see a picture of OHWX Panther. This OHWX is the special token, which you can actually select your own, but it needs to be a sequence of letters, which is rarely used in our human language. And then you will use it as an anchor to train your specific object or subject or style into your network. So what you do then, and the approach I'm describing is called Dream Boost. With the text encoder, you create text embeddings. And with the training sample, again, using the noise scheduler, you create two noisy samples. One very noisy one, and one a bit less noisier with the step of the scheduler n-1. Once you've done that, you pass your noisy image and text embedding into your diffusion model. And you try to predict a little bit less noisier image. Then you take your less noisy image, because you already know it as a ground truth, and you compare it with the predicted noisy image. And based on that, you update the ways, well, you compute the loss, and you update the gradients of your diffusion model, and you modify the weights of your unit model or diffusion transformer accordingly. There is a different way to do that. You can actually, instead of updating the weights of diffusion model, you can actually modify your text encoder. And when I was experimenting with that 2 years ago, that was the results of my first experiment. I've just took some images from Disney movies, and I tried to create Pink Panther in the style of Disney. It was an old architecture, stable diffusion 1.5 or something. And you see, it's not perfect, but these days it's getting more and more perfect. And but you can still see that this style of Lion King is somehow there already. You can also apply the hybrid approach, which means you can actually update the weights of your diffusion model and text encoder. Some approaches use this. And there is another great approach called adapters, specifically low-rank adaptation, or shortly LoRa. In this scenario, you don't modify your original networks, which is often very handy because you download these networks from the open source. Sometimes they're closed, so you cannot even modify them. And then you put this adapter network on top of it. And this adapter network works like a sandwich. So you just inject these layers in between of the layers of the original neural network, and they modify the signal coming through the network. You can also use post-processing of these images relying on text prompts. And here, this is the result which I achieved by simply prompting a model, the same fine-tuned model, applying different fine-tuning prompts and asking for different styles. And you can see that, well, the features are here, but you get very different styles based on that. Another interesting observation was that the punctuation of prompts actually matter. So I've experimented by taking this bare prompt and applying it on the same network, the same image, and just a simple use or not use of commas yields very different results. Another interesting observation was that there is some bias associated with prompts. And well, in the first example, in the upper row, I've asked the image to generate New York in the background, and it provided me with a Western face. Then I used the very same prompt, but I asked for Chinatown in the background, and the person was looking more Asian. Interestingly, you can actually apply the technique called prompt blending, where you can add weights to specific keywords, and then you can interpolate between different results, right? It also was the case when I was using names of artists. You can actually look up names of artistic styles online. And when applying artistic style with an artist with a Western name, it was more Western, and when I used an Asian name, it provided me with an Asian result. And then I applied prompt blending, and the result was also very interesting. There are also zero-shot approaches, meaning that you don't need to train your network at all. You do just like facial recognition, you extract embeddings from your face, and then you inject these embeddings into the diffusion model, and this could also lead to interesting results. The downside of this is that you will always get your portrait in the same angle, and you cannot change facial emotions, but for a quick edit, it's also fun and works really well. And to end my part of presentation, I'd like to show you what we as NVIDIA are working on. The model we are working, it's actually a family of models. It's called Edify. And these are foundation models to create different visual content. We have Edify for image generation, so you can create images in high resolution. In the first iteration, we've trained it with our partners Getty Images on the legally sourced data, so you can be sure that the model is free of bias as much as possible. We also have a video and 3D generation, and I'm proud to tell you that I'm contributing into text-to-video model. It will be open-sourced very soon. In this system, you can also create, 3D objects, and you can populate digital twins, as I mentioned before. So it's very exciting where this technology can bring us, and it's getting better and better, and I'm really excited to see what comes next.